Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The distinguished lecture series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome.
It's a pleasure and an honor to introduce Mladen Bestvina, Distinguished Professor of Mathematics at Utah and one of the fearless leaders of geometric group theory in the world today. If I am to even summarize and give even a glimpse of the range and depth of his work, I don't think 2 minutes would be possible, would suffice, but I'll try nevertheless. So he started off by giving a complete understanding of high dimensional Menger compacta. In the early 90s, along with Mark Fain, he proved what has become the archetypal combination theorem in the context of geometric group theory, spawned a huge amount of work subsequently in the last 20 years and keeps spawning work. And this is an opportunity for me to record a personal intellectual debt to this magnificent piece of work, something many of us return to time and again to derive nourishment. Subsequently, he went on to furnish an account of the Rips machine for group actions on R-trees, developed a Morse theory in the simplicial context for CAD0 cube complexes. And then there was a series of papers on OutFN, brought OutFN, outer automorphism groups of the free group, into the broad context that contains mapping class groups and non-uniform lattices in semi-simple E groups. This work had started earlier with his resolution of the Scott conjecture and bringing in the technology of train tracks into this context. And then he went on to prove the Tietz alternative and essentially brought this thing into mathematical mainstream, the dynamics on free groups. I'll jump over a bunch of years here and just allude to a relatively recent piece of work which is related to the talk he is giving about finiteness of asymptotic dimension, joint work with Ken Bromberg and Koji Fujiwara, where he proved finite asymptotic dimension of mapping class groups. So finite asymptotic dimension is a large-scale geometric group theory analog of topological dimension, and this theorem has implications for the Novikov conjecture. I could go on and on, but in the interest of time, let me stop this here and just say that Mladen's work, its range and its depth have been recognized first, amongst many other recognitions that he's received. In 2002, he was an invited speaker at the ICM in Beijing, and in the upcoming ICM in 2022, he is an invited plenary speaker. All yours, Mladen. You do us all proud.
All right. Hello, India. Hello, Mahan. It's sort of weird to talk into a computer with no audience, but I hope you enjoy it. So I thought I would talk about asymptotic dimension. This is a large-scale invariant of metric spaces introduced by Gromov. And the reason I want to talk about it is because one of my favorite questions that I'd like to either answer myself or I'd like to see somebody else answer involves asymptotic dimension. Okay, so let's start at the beginning. This will be mostly about just basics of asymptotic dimension. And if I get a chance at the end, maybe I'll say more about this problem. Okay, so so X is a metric space, and the motivation for this definition is just a classical topology, classical notion of covering dimension. So to recall that, the covering dimension of this metric space X is less than or equal to n if for every epsilon you can find an open cover of X, so that all these open sets have diameter less than epsilon, and every X is contained in at most n plus 1 of the U alphas. Okay, so this is really the same as saying that the nerve of the cover is at most n-dimensional. And the nerve of the cover is a simplicial complex that consists of the vertices that correspond to the U alphas, and simplices correspond to non-empty intersections. Okay, so that's a very classical definition. And of course, here epsilon, you should think of epsilon as being small. And in the asymptotic dimension, large-scale geometry, this number epsilon is replaced by r, and r is going to be a large number. Okay, so the asymptotic dimension of a metric space X is less than or equal to n. If for every r, radius r, you can find a cover here, you don't have to say open cover, it's just an old cover, U alpha of X, so that the diameters of the U alphas are uniformly bounded. Okay, so they can be very large, but they just have to be uniformly bounded. And every R ball intersects at most n plus 1 of the U alphas. Okay, so the picture here, this picture below, proves that the plane has both the covering dimension less than or equal to 2 and asymptotic dimension less than or equal to 2. In the first case, you should think of these bricks. So it's a tiling of the plane by bricks, by rectangles, and it's done in such a way that every point belongs to at most 3 bricks. And in the first case, you want to replace the bricks by a slight neighborhood. So that's what these red sets are. So you just think about that as being some kind of epsilon neighborhood, and the bricks are really small. So these red sets are also really small, and every point is contained in at most 3 of them. In fact, every little ball, as long as the ball is sufficiently small, is going to intersect at most 3 of these red sets. And for the asymptotic dimension, you just think about blowing up this picture, scaling it up so that the blue ball, you think of the blue ball as having radius r. So any place you position this ball, wherever the center is, as long as the radius is the same, will intersect at most 3 of them, 3 of the bricks. Okay, and then of course you say that asymptotic dimension is equal to n if it's less than or equal to n, and it's not less than or equal to n minus 1. Right, so that's a somewhat usual way people define dimension. Okay, the basic properties or basic theory of asymptotic dimension was developed by Bell and Dernyshnikov, and they have 2 or 3 theorems that they're important and that they're used all the time in this business. And so I'm just going to go through these theorems. So the first one is the product theorem. This is also exactly analogous to the classical covering dimension. So if you have 2 spaces, X and Y, then their product, the asymptotic dimension of the product is less than or equal than the sum of the asymptotic dimensions. Surprisingly, in at least in the classical dimension theory, there are examples where strict inequality holds. Okay, so if you erase AS in all three places, this is a theorem, but equality may not hold. Okay, there are examples where, in fact, you can even take x equals y, surprisingly. So there are spaces whose dimension is, I believe, 2, and when you take x squared, the dimension is 3. Even compact metrizable spaces. Okay, but anyway, here we are really mostly concerned with upper bounds, and in fact, we'd like to figure out if spaces have finite or infinite asymptotic dimension. So it's a very crude kind of discussion. One thing that the motivation for Gromov was that this notion has is a quasi-symmetry invariant. If two spaces are quasi-asymmetric, then they have the same asymptotic dimension. So, for example, z to the n and r to the n are quasi-asymmetric, and they have the same dimension n. And you can, from the product theorem, you can see immediately that the asymptotic dimension of Rn is less than or equal to n, or you can also give a brick proof of the same fact. In fact, asymptotic dimension of Rn is equal to n, and you prove this in the same way that you prove that the dimension is equal to n. Namely, if you had a cover that witnessed the fact that Rn has dimension less than or equal to n minus 1, then you would factor the identity map on Rn through or coarsely up to a bounded error. You would factor it through a simplicial complex of dimension n minus 1, and that's not possible because you have the fundamental class, so it would violate non-zero class factors through 0 kind of proof. Okay, so in fact, this is invariant not only under quasi-asymmetries, but under coarse equivalence. A quasi-isometry is one, I wrote the definition down here. You have a linear bound on the lower bound and the upper bound between the distance between the images of the function. You have a function from x to y, it's a quasi-isometry. If there's a linear bound, both lower and upper bound, on the distance in the image between the 2 points in terms of the distance in the source. But in the coarse equivalence, you dispense with the requirement that these are linear functions. They just have to go to infinity. They have to be functions from R to R, from R plus to R plus, that go to infinity with the variable. Okay, and if you have two metric spaces that are coarse equivalent, then they'll have the same asymptotic dimension. So some of the point is that uniformly bounded sets are mapped to uniformly bounded sets. And so if you just inspect the definition, you see that that's good enough. Okay. Okay, so let's continue with the basic properties of asymptotic dimension. There is the union theorem of Bell and Reznichenko. So here you want to consider this tree, really. So there's the x-axis, and then there are these vertical lines in the plane that intersect the x-axis at the integer points, for example. And you want to equip this with the path metric, right? If you just take the induced metric from the plane, then this object would be quasi-asymmetric to the plane, and it would have asymptotic dimension 2. But with the path metric, it's a tree, and it'll have asymptotic dimension 1. And you can use this union theorem to see that. Okay, so here in the union theorem, it's an infinite union. You have the space X, and it's an infinite union of lines. Okay, infinite union of these X alphas. And what we're assuming is that all these X alphas have asymptotic dimension less than or equal to n uniformly. What I mean by this is that if you look at the definition of asymptotic dimension less than or equal to n, well, there is some, for every r, there is an open cover, or sorry, for every r, there is a cover u alpha with diameters uniformly bounded. Well, I want this uniform bound to be the same for all x alphas. Okay, that's what I mean by they have asymptotic dimension less than or equal to n uniformly. So of course, if they're all isometric to each other, then that's a redundant requirement. Of course, these constants will be the same for all of them. And that's the case in our example. So it's just a union of lines, infinite union of lines. Okay, so that's one assumption, that all these x alphas have asymptotic dimension less than or equal to 1, or n in this case. And then for every r, you should have a subset, y sub r. And in this picture, this is the red set. So it's the x-axis together with the something like the r neighborhood of the x-axis. So you take these little intervals, okay, or together with the x-axis. That's my set y sub r. And I want to know that the asymptotic dimension of y sub r is less than or equal to n, and n is 1 for us. And also that if you look at the what's left of each x alpha, that should be r separated. So what's left of x alpha is right, it's the complements of these red set, the complement of the red set. So here's a typical x alpha, and I'm deleting the red set. So I'm getting these little two rays. And if I take two different alphas, well, the distance between what's left is it's more than 2r. The distance, you have to go all the way down to the x-axis and then go over here, but that distance is more than r because I took the r neighborhood here of the x-axis. Okay, so these sets are separated, and then the conclusion is that the asymptotic dimension of the whole space is less than or equal to 1 in this case. Okay, so that's another very useful theorem. And then this is the one that's most useful. This is called Bild-Ranishnikov's Hurevich theorem. It's called the Hurevich theorem because the classical dimension, topological dimension theory equivalent, it was proved by Hurevich a very long time ago. I didn't look up the date, but probably in the 30s. And maybe I'll state it over here just for comparison. It's simplest if spaces are compact and metrizable, although it holds in some larger category. But anyway, so suppose you have a f from x to y. These are compact metrizable, and you assume that the dimension of f inverse of y, so all the point inverses have dimension less than or equal to n. Well, then the dimension of topological dimension of x is less than or equal than dimension of y plus n. So you cannot increase the dimension of x. X cannot have dimension larger than what the dimension of y is plus the dimension of the largest dimension of the point inverse. Okay, and the asymptotic dimension analog is actually a little bit more complicated. So here, instead of having compact metrizable spaces, you have just metric spaces because these are interested in large-scale geometry. But F is going to be a Lipschitz map. Okay, so it's an extra assumption. That's kind of what corresponds to continuity in the classical case. It's a Lipschitz map. And okay, X is a geodesic space. That's not a big deal. That's just a technical assumption. Okay, geodesic space. And now here, that's what's slightly more complicated is that we don't look at just point inverses. We have to look at the thick point inverses, namely inverse images of balls. Okay, so you take for every r, right? For every r, even large r, you look at the family of these of these ball inverses, right? So they're kind of thick point inverses. And you want to know that these point inverses have, so in the classical case, you want to know point inverses have dimension less than or equal to n. Here, you want to know that asymptotic dimension of these thick inverses is less than or equal to n uniformly. Okay, in the same sense as before. So the uniform constants. Then the conclusion is the same, that the asymptotic dimension of x is less than or equal to the asymptotic dimension of y plus n. Okay. So this is sometimes the case for these Lipschitz vibrations, that they look like locally look like products. So maybe something like you have a you have these point inverses, and here is the ball of radius r, and you look at the inverse image, and that's just somehow a thickening of one of the point inverses, right? Maybe this is just somehow a Hausdorff neighborhood of one of the point inverses here. And if that's the case, then this more complicated condition can be kind of replaced by the simpler condition that just point inverses have to have asymptotic dimension less than or equal to n. So this is somehow what I said under the first example. Lipschitz vibrations in which here I also, to get uniformity, I'm also going to make the assumption that all inverses of these balls of radius r are isometric to each other. That's not such a crazy assumption if you think about groups, as this next example shows. And then each, so they're isometric to each other, and they're Hausdorff neighborhoods of just f inverse of a point. So that's kind of a simpler situation where this the kind of theorem applies. And this happens if you have a short exact sequence of groups. So of course groups, finitely generated groups are going to be metric spaces, and they'll have asymptotic dimension. And then you can conclude this because this fibration from B to C. I mean, this map from B to C satisfies the assumptions of the Hooray-Rich theorem. It's a Lipschitz map, and these inverse images of balls are really thickenings of the kernel, right, of A. And so you're assuming that A, if the asymptotic dimension of A is less than or equal to n, then the conclusion of the Bell-Denishenkov theorem is exactly this. Okay, so that's another useful kind of thing. Now going back to bricks, right? You can also use that brick technology to show that asymptotic dimension of the hyperbolic plane is 2. And here's the picture, right? So here the brick decomposition, it looks a little bit more complicated, but it's the same sort of idea. So you look at, for example, you look at these circles of radius 5r, 10r, 15r, and so on. And each annulus between two such circles is bricked up with bricks like this. And maybe you have to say some words in exactly how you lay the bricks down, but this can be done. And then it's the same principle holds that any ball of radius r will look like this, and it'll intersect at most. Here it looks like I could have missed it. Here it looks like -4. But anyway, you can arrange these bricks so that they all all these balls of radius r intersect at most 3. And there's actually if you wanted to write down the proof of this, then instead of deciding exactly where to put the bricks, you could also use this Bell-Denishenkov theorem. So what we are doing here is really mapping the hyperbolic plane to a ray. It's kind of like a Morse function where we look at the function that's distance from a base point, from the origin. And then these pre-images of right. So here's the ray, and now what I'm supposed to do is take some kind of a ball of radius r, or 5r, or I don't know. It doesn't really matter. I want to take a pre-image of some interval, and that's what I have to understand to apply this Bell-Denishenkov theorem, and that's exactly one of these annuli, right? And so what you have to see is that all these annuli have asymptotic dimension less than or equal to 1 uniformly, and then that's going to prove, since the ray has asymptotic dimension 1, that will prove that the hyperbolic plane has dimension less than or equal to 2. And yeah, okay. So that's a little exercise. But the point is that these annuli are quasi-isometric with uniform constants to a circle. You can just retract the whole annulus down to one of the components, and that'll be a quasi-isometry with uniform constants. And so you just have to see that circles of arbitrarily large radius have asymptotic dimension. Each circle itself, of course, has asymptotic dimension 0 because it's a bounded set. But you have to make sure that you make the statement uniformly. And so for an increasing sequence of circles, uniformly the asymptotic dimension is 1, right? Because you can cut up each circle into long segments and make sure that these balls of radius r intersect at most 2 of them. Okay, and you can do the same thing with the plane. Well, of course, the plane is r cross r, and so you could just apply the product here. Okay, this is slightly trickier. Asymptotic dimension of the tree is 1. When you first see this, you try to you just apply the definition and decompose the tree into these sets, to find the cover as in the definition. And your first attempt is to find these to try to find the sets that are connected, they're subtrees. Well, then you will fail. So it turns out these sets have to be disconnected. And one way to do this is to again look at the circles whose radius is a multiple of 5r, and then for every vertex that I see on this circle of radius, say 5k minus 1r, right? So this is so we're looking at 3 circles in a row, and for every vertex on the smallest circle, you're going to define a box, one of these sets that live between the other two circles. So between the middle circle and the largest circle. That's going to be this red part of the tree. And you'll notice that it's not connected. It's not a subtree. It's a subforest. And the rule is you look at the points in the tree between the two circles, between the outer circle and the middle circle, so that when you connect these points to the base point, right, you have to pass through this green point. For every vertex, which is the green, well, it started out green, then I made it black. But anyway, for every vertex on this circle here, on the smallest circle, I'm defining a box here, and the rule is I take the points that need to pass through that vertex to get to the base point. Okay, so that's an example of one of the sets. And you'll notice that two such, right? If I take another one over here, which I didn't draw, but they're separated. They're far apart from each other because they have to go two circles down before they can connect up. So the distance between them is at least 10 r or something. So any ball of radius r can intersect at most one of these boxes between two of these circles. And of course, this ball of radius r can also intersect one of the boxes, over here, or maybe one over here. So you can intersect one in each annulus. But it's only radius r. That's much less than the size of the annulus. So in other words, it can intersect at most two of the boxes, and that's exactly the definition of asymptotic dimension less than equal to 1. And you can, another way to think about this is exactly using, like in the case of the hyperbolic plane, you can think of this as being a Morse function from the base point, distance function from the base point, and then you're examining inverses of intervals, and then you have to kind of show that these have uniformly asymptotic dimension 0. And that's somehow the point of that is that these are, they consist of these uniformly bounded sets that are far apart from each other. And that's somehow what makes asymptotic dimension 0. They're well separated and they're uniformly bounded. So that's somehow the reason that they have asymptotic dimension 0. And maybe that's easier to see that way than the argument I gave before. Okay. Okay, and the kind of the last thing is the theorem of Gromov, the original theorem of Gromov, that asymptotic dimension of any hyperbola group is finite. Now, I'll give you the argument in a minute, but the Gromov's argument is really only showing that it's finite. It's not really giving you a sharp estimate on what the asymptotic dimension is. So later, there was a theorem of Buyalo and Lebedeva. Maybe I'll write it over here. That showed that the asymptotic dimension of a hyperbola group is equal, in fact, to the topological dimension of the boundary of the group plus 1. Which is somehow what you would expect. I mean, and so for example, if G is torsion free, then this is exactly the cohomological dimension. So equals the cohomological dimension of G if G is torsion free. Okay, and it's still an open problem whether cohomological dimension, whether asymptotic dimension of a group is equal to the cohomological dimension, at least when they're both finite. We sort of suspect that the answer is no, and that the counterexample might be the mapping class group, where we know the cohomological dimension of a mapping class group of a surface of genus G is something linear in G, and Herrer proved this, and there's an exact number, but I don't remember it. But it's some linear function of G, while asymptotic dimension is shown to be less than is bounded by a quadratic number in G. So, but we don't really know. It could be that we don't have lower bounds for asymptotic dimension. There are of course groups with infinite asymptotic dimension. For example, Thomson's group contains z to the n for every n, and so that means that its asymptotic dimension cannot be smaller than n. for any n. Therefore, it's infinite. Okay. Maybe I should also say that the reason so why do we want to have theorems like this, like the hyperbola groups of finite asymptotic dimension? Well, I think one is just kind of philosophical, that you if you want to claim that you understand the large scale geometry of a group, then you should be able to answer this question, whether the asymptotic dimension is finite. This is kind of like in topology, right? You claim, well, I understand the space, and then it turns out you don't know if it's finite dimensional or infinite dimensional. Then I wouldn't believe you that you understand the space. Okay, so it's kind of like that for groups too. Although maybe asymptotic dimension is harder to compute than topological dimension. Okay, so I wrote down just to remind you the definition of delta hyperbolicity. So you have a geodesic metric space, and every triangle is thin. So you have 3 vertices, and you draw geodesics, and then each side has to be contained in the delta neighborhood of the union of the other 2 sides. Okay. And here are some examples. Free groups. Well, free groups, of course, are quasi-asymmetric to trees, and we already saw that asymptotic dimension of trees is 1. Well, unbounded trees. If a tree is bounded, then of course asymptotic dimension is 0. Okay. Fundamental groups of closed surfaces, as you know, and then of closed hyperbolic manifolds. There are various other examples. Okay, so let's give a sketch of how to prove Gramov's theorem. Okay, so G is a hyperbola group, and we want to prove that asymptotic dimension is finite. And the proof is going to be very similar to that of trees. Okay, so this picture here is in the calligraph of the hyperbola group, and here is the base point, the identity. And I again look at these concentric circles of radius a multiple of 5r. Right, so here they are. And for every vertex on this smallest circle, there are three consecutive such circles, and I look at the smallest one. I look at the vertex there, and I'm going to define this box, right? This set. And how is it defined? Well, the C of V, so that's the set corresponding to the vertex V. So it'll consist of points in the calligraph, so that there is a geodesic to the base point that passes through V. Of course, geodesics are not unique, and so you could have several geodesics, and some pass through V and some pass through other points. But for C of V, I'm taking all points that have at least one geodesic that passes through V and goes to the base point. Okay, so that's the red set. Red set corresponds to this vertex V, and the blue set here is going to correspond to W. So those are the typical boxes that I'm using to cover my calligraph. Okay, so now what you have to see is, if I take a ball of radius r somewhere, then I'd like to know that there's a bound on how many of these boxes this ball can intersect. Okay, so so here's the basic observation, right? If I suppose I have a ball of radius r that intersects both of these boxes. Okay, so then the picture is something like this. You have this vertex from the blue set. And I guess I drew it blue, but maybe it's not easy to see that it's blue. So this point here is supposed to be in the blue set, and this point here is supposed to be in the red set. Okay, and the distance between them is less than or equal to 2r, because we're assuming that this ball of radius r intersects both blue and red. So I'm just picking a point in the ball that's blue and the point in the ball that's red. So the distance between these 2 points is at most 2r, of course, because they're in the same ball of radius r. And then here is the identity, the base point, and then I have these geodesics. One passes through W, and the other one passes through V. Right? And this, so as I said, this distance is less than or equal to 2r, but this distance here is at least 5r, bigger than 5r. Right? This is the distance, from one of these red points to V. I guess it could be equal to 5r, greater than equal here. And likewise over here, this is greater than equal to 5r. Okay, well, just from some basic hyperbolic geometry, you can see that these points V and W are in the thin part of the triangle, right? Every hyperbolic triangle kind of looks like this, right? It has sort of a central region, and then there are these sort of cusps, and a pair of points in a cusp, that, like the distance from that vertex, they are distanced at most 2 delta from each other, or maybe a single delta. Okay, so you conclude here that the distance between V and W is less than or equal to 2 delta. Delta is the constant from hyperbolicity. Okay, so what that shows is that, so how many of these boxes can the ball of radius r intersect? Well, at most, something like the number of points in the ball of radius 2 delta, in one of these layers, in one of the annuli. But then it can also intersect some boxes in the next annulus. So that's why you have to multiply this by 2. And then I don't know why I subtracted 1. But in any case, this is some number that doesn't depend on r, and so this bounds the asymptotic dimension. So I guess because you're allowed, okay, -1 is because of the definition of the asymptotic dimension, right? You take this multiplicity and then you subtract 1. Okay. Let's see how we're doing on time. Actually, I don't remember when I started. Okay, well, then we will go for another 10 or 15 minutes. Okay, so so let's see. Oh, maybe I should, before I start with this, I want to say maybe that it's also known for example, for cat-zero cube complexes. If you take so this is the theorem of Nick Wright, that if you take a cat-zero cube complex of dimension n, so topological dimension, there are n cubes, but there are no cubes of higher dimension, then the asymptotic dimension is also bounded by n, by that same number, which is what you would expect. However, it is open for general cat-zero groups. Okay, so even as far as I know, even something like 2-dimensional, I mean, you make a cat-zero 2 complex made out of, say, triangles, equilateral triangles, and I think it's not known whether asymptotic dimension is finite or not. Okay. Okay. So now I want to explain. So the theorem that I proved with Ken Bromberg and Koji Fujiwara is that mapping class groups have finite asymptotic dimension. And maybe if you know what I do, maybe you can anticipate what my favorite question might be. So out Fn is a group that behaves in many ways like mapping class groups. So you might guess that out Fn also should have finite asymptotic dimension. Well, that is not known, and some of the model what I'd like to follow is the model is this is the proof of mapping class groups. That's how what you normally do when you think about out Fn. There's the mapping class group proof, and then out Fn is usually more difficult, and there are some issues that come up, but anyway, you try to follow the same strategy. Okay, so let me just try to say something about mapping class group. I won't have enough time to get into the details, but maybe I'll lay down some kind of a scene for this. Okay, so the main ingredient here is the curve complex. That's the basic hyperbolic object that the mapping class group acts on. So you have this compact surface, hyperbolic surface, and the curve complex is a simplicial complex, or actually we only really care about one skeleton. So there's just a graph, curve graph. It's somehow easier to say curve complex than to say curve graph. But anyway, the vertices are isotopic classes of essential non-peripheral simple closed curves, or you can think of them as just simple closed geodesics in the hyperbolic surface. And you put an edge between two of them if they're disjoint, if they're represented by disjoint geodesics. And so here is the little portion of the curve graph. There's a purple curve here, and there's a green curve, and the purple and the green curve don't have an edge between them because they intersect. However, the yellow curve and the green curve do have an edge bit because they're disjoint. So this is a little subgraph here on the right of the curve graph. Curve graph is of course infinite, and not only infinite, but it's also locally infinite. Every vertex has infinitely many neighbors. And an example, really the only example we can draw, is the fair graph. And this is not exactly the curve complex the way I defined it, because for a torus, so here I'm thinking the curve complex of the torus, you cannot find two disjoint curves that are both essential and not isotopic to each other. So you relax the definition and you put an edge when the two curves intersect once, which is the minimal possible number of intersection number between two curves that are essential but not isotopic to each other. And then you end up with the failure graph, right? So the vertices somehow correspond to rational numbers, union infinity, and then it's sort of tessellated like this. So you can this when you draw the edges, then you'll naturally get this kind of ideal tessellation of the hyperbolic plane. And you can try to prove, that's kind of a good exercise, try to prove that the failure graph is quasi-isometric to a tree. So the asymptotic dimension of this failure graph is 1. Okay. And here I wrote down some properties of the curve complex. So okay, so the local infinite, I already pointed that out. Here I proved that it's homotopic 1 to a wedge of spheres of dimension 2g minus 2. That's not particularly important for us because we're focusing on the one skeleton. But the key theorem is that it is hyperbolic. And Bell-Fujiwara proved that the asymptotic dimension is finite. And that's somehow a good start. If you want to study the asymptotic dimension of the mapping class group, well, here is a nice space on which the mapping class group is acting, right? And it's acting by acting on these curves. Okay, and maybe I'll also, in the spirit of Gramov's theorem, I'm going to say the outline of the proof of Bell and Fujiwara. It's really, so you're supposed to think about Gramov's proof for hyperbola groups. So if you just try to mimic the Gramov's proof, then you get into trouble because that ball of radius 2 delta, right, will contain infinitely many points. So you're not going to get a useful bound. You'll see that the asymptotic dimension is less than or equal to the number of points in that ball, but that's infinite, so that doesn't really get you anywhere. However, there is this notion of tight geodesics that's due to Mazur and Minsky, and these are special geodesics. Not every geodesic in the curve complex is tight, and in fact, there is a very strong finiteness statement. So any two vertices in the curve complex are joined by a tight geodesic. But not only that, but there are only finitely many tight geodesics joining two vertices in the curve complex. So in general, there will be infinitely many geodesics between 2 points, but only finitely many tight geodesics. And then Bowditch proved an even stronger statement that imagine I don't really want to give a full technical thing, but imagine taking 2 points, say A and B, two vertices in the curve complex, they're far apart. And you look at some sort of ball of some radius, and the radius of the ball is much less than the distance between these 2 points. Okay, and now you look at tight geodesics from a point in this ball over here to a point in this ball here. Okay, so you look at all of them, and you look at some, there's some kind of a midpoint here, and you look at some ball around there of radius maybe 2 delta. They all have to. All these geodesics will have to pass through the ball of radius 2 delta. But if you just look at the tight geodesics, then you'll only see in this ball, you only see finitely many points. They only pass through finitely many points. And not only that, but there's a bound on the number of these points that's independent of A and B and how far they are, as long as they're far enough apart. Okay, so you can repeat Gramov's proof, but instead of looking at all geodesics that join some points to the base point and pass through a vertex, you only look at the tight geodesics. Okay, and then the Gramov's proof just goes through, and you somehow you get a bound on the asymptotic dimension that's basically this Bowditch bound on the number of points in this ball that belong to some tight geodesic from a point on the left to a point on the right. Okay. Now I didn't prepare slides for the rest of the proof, I'm just going to say it quickly. So there's something called the projection complex technology, the projection complexes. And you can use this technology to build a space that's a bit, you take all these curve complexes. They all have finite asymptotic dimension, and you can put them together in some kind of a tree-like fashion. So there's a sequence. So x1, x2, I don't know, x some finite number xn of hyperbolic spaces. So there exist hyperbolic spaces. So each xi is a tree or a quasi tree. I don't know, tree of curve complexes. And the asymptotic dimension of each of these xi's is finite. So the proof that the asymptotic dimension of xi's is finite uses the Hurevich theorem, the Bell-Dranishnikov-Hurevich theorem. It's a quasi tree of curve complexes, and you can crush the curve complexes to points, and you get a quasi tree. And the quasi tree is quasi-asymmetric to a tree, so it has asymptotic dimension 1, and all these curve complexes have finite asymptotic dimension. There are only finitely many types of them, so each curve complex is associated to a subsurface of your big surface. This uses something called Maser-Minsky projections, which I don't want to go into, but anyway, there are only finitely many isometry types of these curve complexes that we're considering, so everything is uniform. All these asymptotic dimensions are going to be uniformly finite. And so from the Hurevich theorem, we see that the asymptotic dimension of these xi's is finite. And then we show that the mapping class group is going to act on this product. And the orbit maps are quasi-asymmetric embeddings. QI embeddings. Okay, so if you know more about mapping class groups, then this really amounts to the Maser-Minsky distance formula. Okay, so this is a very crude outline, but this shows that mapping class groups, so they quasi-asymmetrically embed in the product of these spaces. Each of them has finite asymptotic dimension, so the product has finite asymptotic dimension by the product theorem, and therefore the mapping class group also has finite asymptotic dimension. Okay, but now, so so what about out Fn? That's my favorite question. And there are many pieces that are missing from this picture if you want to carry out the same argument. And this is what I like about this question, because it motivates little sub-questions that you can actually think about. So for example, the starting point is the finite asymptotic dimension of the curve complex. Well, there are several analogs of the curve complex in the out Fn world. So there are various complexes that are hyperbolic, and out Fn acts on them. So maybe I'll just define one of them, and I will maybe I'll finish by asking whether that complex is finite asymptotic dimension. We just don't know. So here's maybe the free splitting complex. Again, that's maybe easiest to define. There are various other complexes. Free splitting complex of Fn. You can look at cyclic splittings. For example, if you have a simple closed curve in a surface, then on the level of pi1, this will define a splitting over Z. So you could analogously talk about splittings over cyclic subgroups of Fn. If you have an arc, if you have a surface and boundary and an arc in it, then that's going to define a free splitting of the fundamental group of the surface. So this complex is more like the arc complex than like the curve complex. But anyway, so how would you define it? Well, a vertex is a free splitting. Let's call it the one edge splitting of Fn. So you can have either something like this, where this is 1. So in other words, you're writing Fn as a free product of A and B. Or your splitting can look like this. It could be A and then 1 like this. So in other words, Fn here is an H&N extension, but it has to be an H&N extension over the trivial. So the edge groups are trivial here. So it's in terms of Basser theory, you're looking at actions of Fn on simplicial trees with 1 orbit of edges, and the edge stabilizers should be trivial. Okay, so these are the vertices. And what are the edges? So an edge is a 2-edge splitting. And then you can also see how to put in higher simplices. 2-edge splitting of Fn. So for example, if I have something like this, here's A, here's B, here's C. So in other words, I'm writing Fn as a free product of A, B, and C. Well, so that's an edge, but what are the endpoints of the edge? Well, you collapse one edge at a time. So you can collapse, for example, this left edge, and you'll end up with, so A star B here, and then C here, or you can collapse the other edge. So then you'll get, A, and then B star C. Okay, so you put an edge between these two particular splittings. And then there are also other 2-edge splittings. I mean, you can also have this kind of a 2-edge splitting, or you can have this kind, and maybe there are a few others. Okay. Okay, so the basic question is so let's call this FSN. So this is the complex. And there's a theorem of Handel and Moser that says that FSN is hyperbolic. And then the question is the big question that, so this is the kind of thing that I'd like to know before I retire. So is asymptotic dimension of FSN finite? And that would, if you can prove that, then that would give you some kind of a starting point in this strategy. Even if this is known, you wouldn't, it wouldn't follow that out of N is finite asymptotic dimension, and that's because we don't have the Maser-Minsky distance formula. So we can build those kinds of spaces, the x1 through xn or whatever it's called, but we wouldn't, and we would have an action, so we'd have an orbit map, but the orbit map wouldn't be a quasi-asymptotic embedding. So there would still be more work to do. Maybe I'll also finish by saying that another reason for knowing that asymptotic dimension of a group is finite is that it implies something called a Novikov conjecture in manifold theory. So and this is kind of a different subject, and maybe not many people know about this, but anyway, this is also very classical. It's a manifold, a smooth manifold is going to have Pontryagin classes, and some of the Novikov conjecture restricts where the Pontryagin classes are elements in cohomology. And the Novikov conjecture restricts where these Pontryagin classes can be in the cohomology ring of a manifold, depending on the fundamental group of the manifold. It's a very important conjecture in manifold topology, and if you can prove that the asymptotic dimension of a group is finite, then Novikov conjecture follows. For example, hyperbola groups satisfy the Novikov conjecture because they'll have finite asymptotic dimension. Okay, so I hope you got something out of this, and I guess the plan is to have a question and answer session at some point. So I'll see you then. Thank you.